Hey Sander, sorry for being late. Did you finish our homework already?
No worries. And no, I haven't finished it. Actually, I'm doing a problem right now. Would you mind helping me? It's problem 3.16.
Sure, I can help you. I just finished that problem this morning.
Okay, an engineer puts her 20-kilogram daughter in an empty cart that weighs 5 kilograms. She then gets a 2-meter-long rope and attaches it to the cart. She holds the other end of the rope and starts spinning the cart around in a circle. A. How many revolutions per minute does the cart make if the tension in the rope is 100 newtons? Assume that the rope is parallel to the ground and that there is no friction. B. Now let's assume the presence of friction if the initial angular velocity is 3 radians per second. What is the angular velocity of the cart after 2 seconds? The coefficient of static friction between the cart and the ground is 0.4, and the coefficient of kinetic friction is 0.2. Alright, so how do we even start this problem?
Well, what I did first was to list the knowns and unknowns.
Okay, so simple enough. We know that the mass of the daughter is 20 kilograms, and the mass of the cart is 5 kilograms, and that the rope creates a circle with a radius of 2 meters. We also know that the tension of the rope is 100 newtons. In part A, we want to find the cart's revolutions per minute, assuming there's no friction. And in part B, we want to find the angular velocity after 2 seconds. And now we assume there is friction.
Perfect. But I would also suggest to draw a sketch to help you.
Okay, is this where I draw the free body diagram, right?
Yes, we always draw a free body diagram.
So should I draw the free body diagram from the top view or the side view?
I used the side view because it helped me see the 3 forces.
You're right. Let me do it from the side view. We have the tension of the rope on the cart, the normal force by the ground on the cart, and the weight of the cart. But wouldn't the top view help me solve for friction and tangential acceleration?
Yes, you're right. And we will use it to solve part B.
So we know the normal force and the weight must cancel out because there's no acceleration in the vertical direction, right?
Yeah, I thought the same thing. Now there is a net force in the R direction. It's the tension.
Okay, and is this tension the centripetal force, the one that makes the cart go around?
Yep, the net force in the R direction is just the tension. So F net equals the tension equals the mass times velocity squared over R. So that means all we need to do is solve for velocity.
But I think we need to use the equation with the angular velocity omega instead, because the problem asks for revolutions per second. So tension equals mass times the angular velocity squared times the radius.
Well, that's not how I did it. First, I found the velocity in meters per second, and then found the angular velocity. But let's see if we find the same number.
So calculating it out, I got omega equals 1.41 radians per second. Alright, so let's do part B.
Whoa, not too fast. The problem asks for RPM, not radians per second.
Oh, right. So I know that there are 2 pi radians for every 1 revolution, and there are 60 seconds to every minute. So the radians cancel out, and then the seconds cancel out, which leaves us with 13.46 revolutions per minute. Thanks, Anne-Marie.
Don't mention it. Now on to part B.
Okay, so part B. This time we have to include friction. Oh wait, they gave us 2 coefficients of friction. Which should we use?
Since the cart is rubbing against the ground, we should use the kinetic coefficient of friction.
I see. Alright, so next is to draw the free body diagram. So the side RZ axis doesn't change, but this time we also need the top view, the RT axis. The tension is in the direction of the R axis again, and now we have the force of friction opposing the motion in the tangential direction. The normal force and the weight are there, but we can't see them from the top view.
Correct. Since we are given friction, which is tangential to circular motion, we know that the force is on the t-axis. That means we just need to find the net force in the t direction to find the tangential acceleration. Do you know which force that is?
The force of friction, right? Mu times the normal force? It's the net force that slows down the cart. So the force of friction equals mass times tangential acceleration. I believe that once we find the tangential acceleration, we can find our angular acceleration by dividing the tangential acceleration with the radius.
Yeah, I got the same thing, but don't forget that the cart is slowing down because friction is always pointing opposite to the motion. Since we considered the velocity to be positive, the acceleration must be negative.
Then all we have to do is use kinematics and circular motion. Part B gives us both the initial angular speed and time, so we need to find the equation that has both values. Let's use this one. The final angular velocity equals the initial angular velocity plus the angular acceleration times the elapsed time. So it's 3 radians per second plus negative 0.98 radians per second squared times 2 seconds, which gives us 1.036 radians per second.
And that makes sense because it is slower than the initial 3 radians per second.
All right, let's do one more problem. Here, you pick the next one.
Okay, sure.